6, 7, 8, 9. So we have 9 registered participants. No, 1, 2, 3, 4, 5, 6, 7. So 7 registered participants from India, 2 registered participants from Indonesia, 1, 2, 3, 4, 4 registered participants from Kuwait, and the rest from the Philippines. So how many all in all registered? So 248 participants registered for the event. So to those who are not here, so maybe they are joining this event through live stream in YouTube. Okay, so let's go to the universities. So where are our participants coming from based on the university? So let me sort it ascending. So we have from Department of Education, Alejandro E. Honda National High School. So we have from Son University. Sorry, I cannot mention all of the institutions. So only those who are many. Okay. So we have from Batangas State University. So we have from Bulacan State University, welcome. So Catanduanes State University, Cavite State University, Cebu Normal University main campus, of course from Central Luzon State University, Central Bicol State University of Agriculture, De La Salle University, Department of Education, Gordon College, Holy Name University, Isabela State University, Islamic Institute of the Philippines. Okay, so we have from Manuel S. Inverga University Foundation, Mapua University, Mariano Marcos State University, Mindanao State University, Montessori di Sagadra Familia National University, East Ortigas National University, Clark, Dasmariñas National University, Philippines, Nueva Ecija, University of Science and Technology, Pampanga State University, Philippine High School for the Arts. So welcome. Rizal National High School. So we have from Southern Luzon State University. So we have from Tarlac State University, University of Santo Tomas, University of Didagupan, University of Caloocan City, University of Mindanao. So to our brothers and sisters from Mindanao, so hello and welcome. University of Northern Philippines, University of Southern Philippines, University of the Philippines Baguio, University of the Philippines Silman, University of the Philippines Los Baños. Okay, so there. So we have so many. So most are faculty members. Then there are graduate students and I think undergraduate students. So that's where the participants or the characteristic of the participants in this event. So okay, so let me go to the next one. So let's now call in Dr. John Rafael Antalan, so the president of Mathematical Society of the Philippines Region 3, to introduce to us the speaker. So Dr. Antalan will also serve as the moderator for the talk. So Dr. Antalan, so you now have the floor.
Thank you very much, Sir Melchor, for welcoming our participants. Dear esteemed speakers, brilliant researchers, passionate educators, students, and fellow mathematics enthusiasts, a very warm welcome to all of you. Good morning to those joining us from here in the Philippines, from Indonesia and Vietnam, and a very pleasant day to our participants joining from India, Kuwait, and other parts of the globe. On behalf of the Mathematical Society of the Philippines Region 3 chapter, it is my absolute honor to welcome you to the official launching and inaugural session of the Southeast Asian Series on Mathematics Research, or SEASMR. Today marks a beautiful milestone. What started as a vision to foster regional collaboration has brought together over 200 registered minds today, united by a shared love for numbers, structures, and discovery. This morning, we dive into the fascinating world of current trends in discrete mathematics. What makes the inaugural session deeply special is the span of perspectives we are about to witness. We are privileged to feature the work of both a brilliant beginning mathematics researcher and a highly distinguished seasoned mathematics researcher, showing us that the future of mathematical discovery relies equally on fresh energy and deep expertise. Before we begin our journey into graph theory and matrix design, I would like to express our deepest gratitude to the incredible team who made today possible. First, to our brilliant speakers, Mr. Josh Passion from Central Luzon, Passion Sebastian from Central Luzon State University, and Dr. Pritta Etriana Putri from Institut Teknologi Bandung in Indonesia. Thank you in advance for generously sharing your expertise, your time, and your research with us today. Second, to our visionary initiator, a special heartfelt thanks to Dr. Jonathan Caalim from the University of the Philippines, Diliman, whose spark of inspiration, leadership, and dedication initiated this entire collaborative activity. And third, to our tireless organizing committee, the MSP Region 3 Board of Trustees, Ma'am Yoli, Ma'am Nancy, Sir Mel, Ma'am Jervie, Sir Joe, Sir Eros, Sir Edward, Ma'am Glenda, and again, Sir Jonathan, who have worked tirelessly behind the scenes, upgrading our capacities and ensuring that our community has a seamless space to connect, whether here in our Zoom room or live on YouTube. Mathematics has a unique way of transcending borders. Looking at our screen today, we see a vibrant tapestry of cultures, from Southeast Asia, South Asia, to the Middle East, all speaking the same universal language, the language of mathematics. May today's session spark new questions, inspire new collaborations, and remind us all of the elegant beauty of discrete structures. Once again, welcome to SEASMR. Thank you all for being here, and let us have a wonderful, mathematically enriching morning. So thank you very much. Now, for the second part of my talk, allow me to introduce our first speaker for today's session. It is my distinct pleasure and a matter of great personal pride to introduce our first speaker for this morning's inaugural session. Our speaker is a true homegrown talent of Region 3, hailing from Nampikwan, Nueva Ecija, and a proud member of our very own Mathematical Society of the Philippines Region 3 chapter. I have had the unique privilege of watching his mathematical journey unfold firsthand. First, as his teacher, and now I am incredibly proud to call him my colleague. Just 2 years ago, he graduated from Central Luzon State University with a degree Bachelor of Science in Mathematics, earning distinction cum laude. Driven by a deep passion for the discipline, he pursued advanced studies, and just a few weeks ago, less than 3 weeks to be exact, he successfully finished his Master of Science in Mathematics at the University of the Philippines, Baguio. Today, he continues to give back to his alma mater, serving our community as an inspiring instructor at Central Luzon State University. His research interests thrive at the beautiful intersection of graph theory, combinatorics, and algebra. In his graduate work, he tackled complex structures, exploring inside-out polytopes, and utilizing advanced counting techniques like generating functions through arrangements of hyperplanes. Today, he joins us to share a piece of his brilliant work in discrete mathematics, with talk titled Solving a Graph Coloring Problem Using Geometry and Combinatorics, the Sigma Polynomial of Graphs. Ladies and gentlemen, please join me in giving a warm welcome our colleague, friend, and speaker, Mr. Josh Passion Sebastian. Sir Josh, take it away. Thank you, sir.
Ayan, hello. Ayan. So, good morning, everyone. So, by the way, let me share my screen. Ayan. Ito na po yung screen ko.
Yes, Sir
Hello
Josh.
po. Ayan. So, good morning, everyone. And sabi ni Sir JR, I am Josh Sebastian. And today, I'm going to present part of my thesis, solving a counting problem using geometry, specifically relating to the sigma coloring. So, nag-introduce ako ng bagong concept, the sigma polynomial of a graph. Ayan. So, let me introduce myself first. So, by the way, I am Josh Sebastian. I graduated Gas Mathematics in the Central South State University, batch 2024. And also, I graduated MS Mathematics in the University of the Philippines, Baguio, batch 2026. Yan. So, my field of interest, I currently, so, kailangan ng pointer na. My research interest primarily in geometry, combinatorics, and graph theory. So, there are problems in discrete mathematics that I would like to solve using these three branches of mathematics. So hopefully, by the end of this discussion, makikita natin yung connections nitong tatlong branches of mathematics na to. And if you want to contact me, use my personal email as well as my CLSC2 email as well. Ayan. So for the contents of my discussion, we proceed first with the motivation of my work. So here, we solve a particular geometric problem and we translate this into a coloring problem in graph theory. We also will be meeting the following preliminaries regarding in graph coloring inside polytopes and as well as in the generating functions. Yan. And later, we discuss the constant term of this particular generating function and we apply this in solving the number of integer points inside a polytope. Yan. And then we have an analogous result here. We have the theorem 1 and 2, and then we apply this in solving the sigma polynomial problem, followed by the conclusion and the references. Yeah, so let me start here. Let me start with this quotation. So every branch of mathematics enriches the others, and together they reveal the beauty of the unified discipline. Yeah, so by the end of this discussion, hopefully, makita natin yung connections ng different branches of mathematics. And in solving a problem in one branch, gagamitin natin yung another branch of mathematics. So connected pala yung mga branches of mathematics. Na? So let me start with a motivation. So consider this question. So given the polygon, how can we determine the number of its integer inferior points? So when we say integer inferior points, is integer inferior points having a integer coefficients. Let's have a particular example. We have this rhombus with the vertices 0, 0, 2, 4, 4, 2, and 6, 6 respectively. The green points represent the integer boundary points, while the red points represent the integer points of the polygon. Ayan. So actually, we can solve this general problem using a fixed theorem, which states that the area of a polygon is equal to the number of interior points plus half of the boundary points minus 1. Ayan. So ano ba yung area ng ating rhombus? So the area of the rhombus is the product of its diagonal lengths divided by 2. And in solving this, we have the area of particle. Yan. And the number of boundary points is actually 8, as we can see. No? Ito yung mga green points natin. And using the fixed theorem, we can conclude that there are exactly 11 integer. We have 9 such points. Yeah. So let's consider another problem. So here we have a polygon B, which is a Cartesian product of the closed interval 1 to 4 plus 1 to 4. And then we define the line x minus y equals 0. And here we want to determine the number of interior points in B, but not in the line. Yan. So, we have these endpoints. So, natin bilangan ito mga ito. And as we can see, there are exactly 6 such points. And we claim that each of these points actually correspond to a proper vertex coloring using 1, 2, and 3 colors. Yeah. So from a geometric perspective, we have a graph coloring perspective. Yeah. So hopefully, we are all motivated in my work. So let's proceed to the preliminary section of my study. So we're going to discuss some concepts in graph coloring, polytopes, as well as in the generative function. Let's start. So a vertex coloring is an assignment of colors wherein we can have same color to adjacent vertices of the graph. And if a vertex coloring uses a distinct color, we say that it is a K-vertex coloring or K-coloring of a graph G. Now, we have an analogous term for this. So, ito naman yung K-bracket coloring. So, we define a new terminology. So, this K-bracket coloring uses the colors 1, 2, up to K. Ayan, no? So, pag hambingin natin ito, bro, find the connection between these two coloring. So, when we say K coloring, it uses K distinct colors. And it does not need to be ordered. So, for example, if K is equal to 3, pwede kang gumamit like, for example, 1, 2, and 3. Pwede rin naman si 1, 4, 5, 1, 7, 6. Basta K distinct colors. While in the K bracket coloring, it uses the colors using the subset of this. So 1, 2, up to K. So if K is equal to 3, ang pwede mo lang gamitin is either 1, 2, and 3. So pwede 1 and 2, 1, 3, or 2 and 3. And also, it does not need to use all need colors in 1, 2, up to K. Ayan. Also, we will use the concept of distinctness of two colorings. So we say that 2K bracket coloring C and C prime are distinct if you can find a vertex U such that C of U is not equal to C prime of U. Yeah. So let's have an example for this. So take a look in this graph. So it is a star graph with 5 vertices, and we assign a color 1 here, 1, 5, 3, and 2. And as we can see, we use 4 distinct colors, 1, 3, 4, and 5. So this is a 4 coloring of this particular graph. And since we are using a subset of 1, 2, up to 5 colors, so it is actually a 5 bracket coloring of the graph G. Yan. So you can see the distinction between these two coloring. Yeah. And then next, sigma coloring assigns a colors to which every adjacent vertices satisfy this particular equation. So the color sum of U is not equal to the color sum of V. And for the discussion regarding on the color sum, sigma coloring, and sigma continuity, sigma range, and sigma value, so please refer to the article of Chartrand and Acomodo entitled Sigma Chromatic Number of Graph. So I will give the link for that later. Yeah. And now we define a new concept, the sigma polynomial of the graph. So this particular counting function counts the number of distinct sigma K bracket coloring of the graph G. So take note, dapat ito ay distinct K bracket coloring. Yan. And at the same time, is a sigma coloring. And so we have these two conditions. So actually, our main goal in this discussion is to determine the number of distinct sigma K bracket coloring or the sigma polynomial of some families of graphs, including the path graphs, cycle graphs, even the multipartite graphs, and circulant graphs as well. And so in doing this, we need some terminologies on the polytopes. Ayan. So a polytope in Rn of dimension n is given by this set. So it is a collection of points in Rn satisfying this inequality. So here, A is the coefficient matrix, and then B is the constant vector. So A is an element, is an m by n dimensional matrix with real entries. while B here is an n-dimensional vector with real components. And we discussed this particular polytope, the box polytope BKM in Rn, is a set of points in Rn whose components are between 1 and k. And so let's take a look box polytope in different dimension. So in dimension 1, the box polytope BK1 is actually a closed interval. In dimension 2, the box polytope BK2 is a Cartesian product of two closed intervals. And in general, the box polytope BKN is actually an n-dimensional hypercube with side length of n of k minus 1. Yeah. So moving on, we have this, the hyperplane in Rn is an n-1 dimensional subspace of the following form. So it is a collection of points satisfying this equality, where A here is an n-dimensional vector with real entries. So let's take a look. What is a hyperplane in different dimension? So by the way, in dimension 1, hyperplane actually is just a 0. Diba? 0 lang naman ang magsasatisfy dito. Ax equals 0 in R1. But in R2, the hyperplane actually describes a line passing through the point 0, 0. And in R3, a hyperplane is actually a plane passing through the points 0, 0, and 0. Yan. Next, an arrangement of hyperplane is just a collection of hyperplane. So take note, dapat finite collection of hyperplane. And to form the intersection lattice, we simply take the subset of the arrangement and then we take the intersection of it. So ang elements dapat ito is a intersection of hyperplanes, which we call as flats. So the elements of the intersection lattice is actually flats. Next, to form the intersection semi-lattice, so take note, it is a subset of the intersection lattice, is a collection of flats whose intersection with the polytope is unempty. Yeah. And then this is the concept of inside out polytope. So here we just create a pair of an n-dimensional polytope and an arrangement of hyperplane. And so ito yung gagamitin natin later. So also we will be using this particular counting function relating to the inside out polytope. So given an inside out polytope, we circle and script A. So here, so I is the boundary, the interior points is the interior of the polytope P. So the open the enumerator of this inside out polytope actually counts the number of elements in the discrete set intersection with the interior of P minus the union of the script A. So this particular counting function actually counts the number of all interior of P intersection D that does not lie in any hyperplane. Yan. So if we go back to our example kanina, so meron tayo polytope B and hyperplane H. Yung hyperplane natin in R2 is actually describes a line. So this is hyperplane in R2. Now we can actually write this problem using the concept of open the enumerators. So here we have this inside out polytope, the interior of B, and script A, where script A contains the hyperplane H. And then if we count all interior points of B, excluding those lying in any hyperplane, we have a 6 such points. Yeah. So now from now on, if we see this type of problem, we can use the open the enumerator to simplify and to use symbols. Yeah. So actually, we can apply or use the concept of Mobius function to better solve this problem. So actually, we can write the open the enumerator of the inside out polytope like this. So it is a sum of the product of the Mobius function of 0 hat f times the number of elements in this set the intersection of the discrete set, the integer of B, and the flat F, where the sum is taken over all elements of the intersection semilattice. And for the concept of Mobius function and Hash diagram, so kindly refer to the article of Beck and Soslavsky titled the the inside-out polytopes. Kasi kailangan natin ng Hash diagram for the Mobius function of every flat. Yeah. And also we'll be using this theorem. So ito yung the constant term of a Euler's generating function. So ano ba yung ibig sabihin nito? This actually counts the number of integer points. And to use this, anong gagawin natin? So first, from a polytope, so we have a rational polytope, meaning it's a polytope with rational vertices. And then we write it in this manner. So dapat may sulat mo siya. It is a set of points satisfying this matrix inequality. So we have this coefficient matrix, and this is a constant vector. Now, from this coefficient matrix, the column vectors actually is the C sub I. So C1, C2, and CD are the column vectors of this matrix. And B here is just the constant vector. And once you do that, you take the constant term of this Euler's generating function, and it will give you the number of integer points in P. Yeah. So since we are dealing with generating functions, so let me have some recall or some concepts in generating function. So by the way, a generating function encodes sequence into a formal power series. So from a sequence, we have a particular object with formal power series, wherein so every term in the sequence actually corresponds to a coefficient in this sequence, in this formal power series. So the formal power series of this sequence is actually the sum of a sub n x to the n, where n ranges from 0 to infinity. Ayan. And also, the constant term of a generating function is just the coefficient a sub 0. And we will use this notation const of g of x. So let's have some well-known generating function. So for this sequence, the sequence of 1, 1, 1, 1, 1. So using generating function, we can write it in this manner. So it is a formal power series whose coefficients are all 1. And using some property of the geometric series, you can write it in this way, 1 over 1 over x. So for this particular sequence, 1, 2, and 3, so you can write it as a generating function, 1 all over 1 minus x squared. And for this sequence of triangular numbers, we have this generating function 1 all over 1 minus x cubed. And in general, you can observe this particular sequence, the sequence of n plus k minus 1 to k, for k is equal to 0, 1, 2, up to infinity, corresponds to this generating function 1 all over 1 minus x raised to n. And so later, we will be using this. So moving on, we present the main result of this discussion. So we have three main theorems for data. So the first two, one is the analog of the Euler's generating function. Next, in theorem 2, we apply this theorem in solving the sigma polynomial graphs. And theorem 3 and 4, we show the generating or general form of the sigma polynomial and as well as the generating function. Yeah. So for this first theorem, it's actually the analog of the Euler's generating function. So what ang gusto nitong gawin actually is this counts the number of integer points in this set, the intersection of the box polytope and the flat F, by taking the constant term of this expression. Yan. So, paano natin ito gagamitin? So, syempre, we know that a flat F is intersection of hyperplanes. So, you can write it in this manner. And once you get the coefficient matrix and then the constant vector, so the column vectors of this matrix A is actually this C sub I, so C1, C2, CB. And then the column vector B, ganun siya. Ayan. So once you get the constant term of this, you will get the integer terms in this particular set. And take note, the column vectors here must not be identical to the zero vector. Yeah. So next, in theorem 2. So ito yung practical application of the theorem 1 in solving the sigma polynomial problem. Yeah. So what we have here, so given a graph G, simple graph, with the following vertex set and edge set, and we consider an arbitrary A bracket color C. And we will define the arrangement of hyperplane as follows. So for every hyperplane, we define it as the color sum of VI1 minus the color sum of VI2 equals 0 for every adjacent vertices VI1 and VI2. So if you have, let's say, M edges, you have M hyperplanes as well. Yeah. And after that, you can actually count the number of distinct sigma k bracket coloring of any graph using this formula. So take note, ito yung sa theorem 1, and we just take the product of the Mobius function and this constant, and we take the sum over all plots in the intersection semi-lengths. So actually, there is a general method on computing sigma polynomial of the graph. This utilizes theorem 1 and theorem 2. So let's have this. So in step 1, for a graph G, we like to determine the vertex set, edge set, and the set of neighbors in this graph. So by the way, what is a set of neighbors? So actually, it is just a collection of adjacent vertices to vertex P. And then after that, in step 2, we define this inside-out polytope, the box polytope BKD, and discrete A. And for every adjacent vertices in the graph, we define a hyperplane, sigma of U minus sigma of V equals 0. So by the way, a color sum is just a sum of the colors in the neighborhood of a vertex C. Next, in step 3, reconstruct the intersection semi-lattice, its as diagram, and for every flat F, we compute for these two. The cardinality of the box polytope intersection this discrete set Z to the B intersection with F. And then we compute for the Mobius function of C hat and F. And then in step 4, we actually compute sigma polynomial using theorem 2. Yeah. So let's have a particular example for this. So here we have a graph P4 with the following vertex set and edge set. So from here, actually we can actually compute the set of neighbors and set of the following vertices. So for example, V1 is adjacent to V2, V2 is adjacent to both V1 and V3, V3 is adjacent to V2 and V4, and V4 is adjacent to V3. So we have the following set of neighborhood for every vertices. And then in step 2, we form these inside-out polytopes, and we define the following hyperplane depending on the adjacency of the graph. So we have the following. And then we let x sub I is equal to the color of the vertex Vi, and then we obtain this hyperplane. So actually, these are all equivalent hyperplanes. So we just use another way to write it. Yeah. And then after that, we form the intersection semi-lattice. So by definition, an intersection semi-lattice is a collection of flats such that its intersection with the polytope is non-empty. And once we do that, we have the following flats: 0 hat, hyperplane H1, H2, H3, intersection of H1 and H2, H1 and H3, H2 and H3, and the intersection of H1, H2, and H3. We have the following with the minimum element is equal to R4. So question, so why is the minimum element is actually ambient space? So actually, in the intersection semi-lattice, it is partially ordered by the reverse inclusion. So meaning the minimum element is actually the largest among them. It is the ambient space. And for the Hash diagram, so we have the following. So to actually Hash diagram ang intersection semi-lattice. So as we can see, the minimum element is in the bottom and the maximum element is in the top. So, pinapit ko na rin yung kanilang mga Morris function. So, 1, -1, 1, and -1. Ayan. So, then after that, we compute for the following. We want to determine the number of elements in the intersection of the box polytope, the discrete set, and flat for every flat in the intersection semi-lattice. So, let's consider, let's say, F is equal to the hyperplane H1. So, gaya sabi nun sa theorem, we need to write this plot as a matrix equation. And once you do that, the column vector of the coefficient matrix will be written like this. So, meron kang 1, -1, 1, and -1. And so, actually, we apply only the theorem 1 here. And if you simplify this, you will get the constant term of this is actually k squared minus k cubed minus k squared all over 2. So actually, I already solved it for every flat in the intersection lattice. So ito yung mga values. Ayan. And finally, we apply theorem 2. So we substitute the values of this to solve the sigma polynomial of P4. So therefore we have this. So we have k to the 4 minus 5/3 k cubed plus k squared minus 1/3 k, which is the sigma polynomial of P4. But question, how can we use this? So actually, if you want to determine the number of stick sigma 4 bracket coloring of a graph G, just plug in k is equal to 4 and the value, yun yung gusto mong hanapin. So this actually works for every values of k. So even 100, 1,000, mag-work ito since ito ay polynomial. Ayan. So I actually have some results. So for the sigma polynomial of P3, P4, P5, and P6. So here are the following. So I already calculated the generative function for this. So by the way, for solving the generative function, we use a technique using change of basis. So for a basis of 1, k squared up to k cubed here, we use different bases to come up with this generating function. Yeah. Also, we have the following results for the sigma polynomial of cycle graphs C3, C4, C5, and C6. And as we can see, the sigma polynomial for P5 is actually a piecewise function. So the polynomial depends on the parity of k. So if k is odd, it's the sigma polynomial. For P5 and for k is even, this is the sigma polynomial. Yeah, with the following generating function. So actually, if p is equal to 6, so we have a path graph with 6 vertices, we observe these sigma polynomials. So we have a different sigma polynomial depending on the parity. Okay. So this actually demonstrates the quasi-polynomial behavior of our sigma polynomial. Yeah. So we have this theorem number 3. So this is the general form of our sigma polynomial. It is actually a quasi-polynomial of degree n with the quasi-period of n. So we have n, ito yung parity. No? And take note that each of the components are periodic functions in Q. So the value of these coefficients depends on K. Yeah. So we have this fourth theorem, the general form of the generative function of sigma polynomial, which is actually equal to this ratio, the ratio of the sum of b sub I x and m plus n minus 1 minus I, where the sum is taken from I is equal to 0 to nm plus n minus 1, divided by 1 minus xn raised to n plus 1. Ayan. So nakita natin tong behavior na to kanina. Ayan. So we have other results in sigma polynomial. So here, we connect the sigma polynomial to other existing problems, such as the how can we determine the non-sigma continuous graphs? Ayan. And some types. So, tingnan na lang natin. No? So, by the way, here is the graph invariance property of our sigma polynomial. That is for if two graphs, for every isomorphic graphs G1 and G2, we observe that they will have a same sigma polynomial. And also have this characterization of the sigma range of the graph. So it is actually equal to the minimum value of K, such that the PG of K is greater than 0 for every K is equal to 1, 2, and so on. Also, if a graph G satisfies this particular inequality, we say that G is not a sigma continuous graph. Yeah. So it's actually a way to determine which graphs are non-continuous. And finally, for a simple graph G1 and G2, the sigma polynomial of the graph union of G1 and G2 is actually this product of the individual sigma polynomials. Yeah, so we apply also a graph operation here. Yeah. So for the conclusion, ano ba yung mga establish natin in this discussion? So first, we show theorem 1 and 2. Again, yung 1 is the way to count the number of integer points in the box polytope intersection with the flat. And we apply theorem 1 in solving the sigma polynomial of a graph. Also, we present a method on solving sigma polynomial graphs using theorem 1 and 2. And also, in theorem 3 and 4, we show the general form of the sigma polynomials and its generating function. And finally, we show the relationship between sigma polynomial, sigma continuity, and also we show the graph invariance property of the sigma polynomial. And also, we apply an operation, the graph union. So, ano pa yung mga pwede natin gawin? So, actually, marami pa namang problem na pwede natin gawin in this topic. So, first, we can actually count or find the sigma polynomial of wheel graph, circular, and tree graph. So, actually, in my thesis, I actually counted or computed for the sigma polynomial of the complete graph, as well, some families of complete multipartite graphs, as well as other families of circular graphs. So, open na itong wheel and tree graphs. So, pwede naman kayong gumamit ng ibang types of graphs. Also, you can apply other operations as well, such as the graph, join graph, splitting graph, as well as the partition product of graphs. So, itong third, fully partial na nagawa ko na to, I already created a program to find the sigma polynomial only for path graph and cycle graph. So, for any general graph, so please create this, yeah? For any graph. Yun yung medyo crucial. Ano. And also, using Ehrhart theory, make another method on computing the sigma polynomial graph. And finally, ito yung bumabagabag sa akin ngayon. So, please extend the idea of sigma polynomial to the sigma symmetric polynomials of graph. And so, for the symmetric polynomials, so available naman sa internet. So, mag-explore na lang kayo. Yan. So, for the references, here are the following references. I mainly use this introduction to algebraic graph theory and this computing in continuous discretely, as well as this the inside out polytopes and the sigma chromatic number of a graph. Ayan. So I hope you learned something from this lecture. So thank you for listening.
So thank you very much, Sir Josh, for the very insightful presentation. Thank you, sir. Now, at this point, the virtual floor is open for your questions. Due to time constraint, sirs and ma'ams, dear participants, we may cater only to questions. And if you have further questions, you may email Sir Josh via the email he presented earlier. So while waiting for question, you may type your question now, dear participants. While waiting for other question, I prepared one question for you, Sir Josh.
Yes, sir.
In your presentation, sir, you use constant term of a certain specific multi-variable generating function and
Yes,
the
sir.
concept of inside-out polytope, no, in determining the sigma polynomial of path and cycle. But take note for certain order, 3 up to 6 for path and 3 up to 5 for the cycle. However, in your abstract, you use another method in determining the sigma polynomial of paths and cycle for higher order. My main question is, I am just wondering the motivation for deviating from the first method to the second method with regard to higher order paths and cycles.
So actually about that, I already created a method for higher order of graphs. So for graph, let's say P6, P7 up to P12. So for that, I created a new method. So actually it involves the concept of the neighborhood or the difference, you know, the difference matrix of a graph. So using that, you can actually compute for the quasi-periodicity, quasi-period of a graph. And once you do that, you can actually compute for higher order. Yeah. So due to time constraints, so hindi po natin siya na-discuss dito. Yeah.
Okay.
So pwede ko naman i-share if ever na kailangan mo.
Thank you very much, Sir Josh. Another question, sir, is being raised actually by a certain individual that is present here in this Zoom meeting. The question is, can the method be expanded into other type of graph coloring?
About that, sir, I think pwede, sir. Kasi ang kailangan mo lang dito is just how can you describe this type of problem using this sigma or the inside out polytope. So yung translation po yun, depende na po sa inyo.
Okay,
Yeah.
thank you very much,
Thank
Sir
you,
Josh.
sir. Possible, sir.
Thank you, sir. Having no more questions in the chat box. Again, thank you very much, Sir Josh, and I'll give
thank you,
the
sir.
floor back. Thank you, Sir Josh. Floor back to our moderator, to our host, Sir Melchor Kupatan.
Okay, hello. Thank you very much, Sir JR. And thank you very much for our speaker, Mr. Jos Sebastian, so our part-time faculty member here at the Department of Mathematics and Physics. Thank you for your effort and time. So based on the program, we're going to have a kind of community break for 10 minutes. So in this community break, I'll be presenting the MSP Region 3 membership promotion. So I'll start sharing my screen. So I watched earlier a crash course on how to share a slide in Zoom via YouTube. So let me try doing it because I'm not used to sharing my slides. here in Zoom. So, but I think Ma'am Jervy already have it. Ma'am Jervy, can you present my slides? Or yeah, let me try presenting my slides. Uh, so okay, it's better, Ma'am Jervy. Could you present my slides? Because again, I am having difficulty. There. Okay, thank you very much. So I'm not used to sharing my slides via Zoom. So what I'm used to is sharing my slides through Google Meet. So I apologize. So I'll do this for 5 minutes only. So my short talk is about MSP Region 3 membership promotion. So next slide, please. Okay, thank you. So first, what is Mathematical Society of the Philippines? For a few students who are not aware of Mathematical Society of the Philippines, Mathematical Society of the Philippines is the Philippines' premier professional organization dedicated to the promotion of mathematics research in education in the country. Founded in 1973, it has grown from a small Manila-based group of math educators to a nationwide network of individuals with chapters in the three island groups, Luzon, Visayas, and Mindanao. So Region 3 is the one of the youngest chapter. The MSP has represented the country in the International Mathematical Union since 1978. Next slide, please. So what are the objectives of the society? So there are three objectives. So promote interest and awareness of mathematics and its applications, propagate knowledge in mathematics and mathematics education, and third, promote mathematical research. Next slide, please. So what are the benefits of becoming a member of the society? So eligibility for a possible research grant of 100,000. I think this one is for graduate students taking up masteral or PhD. So discount in the registration fee in the national and regional convention, of course, of the Mathematical Society of the Philippines. Automatic membership in the Southeast Asian Mathematical Society. Okay, possible source of points for promotion and inclusion of the memberships in the curriculum vitae. So yeah, I think this would make your curriculum vitae look better. So if you have these items, so example, so in the right hand, so you have research grant there. So under eligibility, what's the number one? Applicant must be a regular member of MSP of good standing. So there. So it's being a member will make you eligible for a possible research grant. So that's on the left-hand side. So on the right-hand side, if you see there, so the one in the red box, so MSP member, 5,600, non-member, so 6,600. So there's a discount if you are a member of MSP if you join the national and regional national convention. Next slide, please. So that one is a photo of the recent 2026 MSP National Convention. So there, so we are a big happy family. Okay, next slide, please. So this one is our photo of the recent convention and General Assembly of MSP Region 3, so held here in Central Luzon State University. So that one is our first ever face-to-face national convention. Next slide, please. Okay, so what is the eligibility for the membership of the society? So how could you be eligible? So those who have taken and passed calculus in college and taught at least a senior high school mathematics subject or engaged in research on mathematics, its applications, or its teaching may apply for regular membership in the organization. So there. So I think it's clear and self-explanatory. So how about for undergraduate students? Undergraduate students in their senior year or graduate students enrolled in graduate programs of mathematics or allied fields may apply for associate membership. So there are two types of membership, regular and associate. Okay. So next slide, please. So when applying for MSP membership, applicants may choose to be affiliated to the MSP regional chapter in the geographical region of their residence. If there is none, they may apply at a neighboring MSP regional chapter of their preference. Okay, next slide, please. So how do you become an MSP member? So yeah, 3 steps. So go to the Facebook page of the Mathematical Society of the Philippines. Look for a featured post about the MSP membership application. And third, click the link and fill out the application form. So very briefly, so let me walk you through how to do it. So next slide, please. So there, so that is the MSP Mathematical Society of the Philippines Facebook page. So at the the third one. So inside the red box, so you have there the featured post on membership. So you have to click it. Once you click it, so next slide, please. Yeah, you will get into this one. So important announcement. So MSP membership application. So there are 2 links there. So new member and renewal. Of course, if you are renewing, I think you already know the process. That's for new member, you have to click the link. So the link it's safe. It's not scam like it will get your bank information. Not like that. Okay, it's safe. Okay, next slide, please. So if you click the link, so it will lead you into this one. So MSP member application form. So there, and you fill out some of the information. So next slide, please. So for more information, so visit the for more information about the Mathematical Society of the Philippines, you may visit the homepage of Mathematical Society of the Philippines. So that's the link. Then Facebook page of the Mathematical Society of the Philippines. That's the link. Next slide, please. Okay, we have also a Facebook page of the Mathematical Society of the Philippines, Region 3. So that's our chapter. Then, YouTube channel, Mathematical Society of the Philippines, Region 3, where this event via Zoom meeting is currently being live streamed. So next slide, please. So that's all I have to say, and thank you very much for your time. Yeah, that's 6 minutes. Yeah. So thank you very much for your time. So Sir JR, do you want to go to the next talk?
Yes, sir. We may proceed now, sir. Thank you, sir.
Okay, so with the permission of our president, so let's now proceed to the next talk. So our speaker will be introduced by Dr. Jonathan Caalim. So Dr. Jonathan Caalim is an associate professor of mathematics at the University of the Philippines, Diliman. So he will be introducing our speaker, Dr. Pritta Putri. So Sir Jonathan, you have the floor. Thank you very much.
Okay. Good morning, everyone. It is my great privilege to introduce our next speaker, Dr. Pritta Etriana Putri. Dr. Putri is an associate professor at the Faculty of Mathematics and Natural Sciences of the Institut Teknologi, Bandung, in Indonesia. Dr. Putri specializes in combinatorial mathematics with research interests spanning design theory, especially Hadamard matrices. She earned her doctoral degree in mathematics from Tohoku University in Japan. Also, Dr. Putri holds double master's degrees from Kanazawa University in Japan and from Institut Teknologi Bandung in Indonesia. She has presented her research at international conferences in Japan and Australia, and actively contributes to the Indonesian Mathematical Society and the Indonesian Combinatorics Society. Beyond research, she has coordinated academic programs, summer schools, and student development initiatives at ITB, and was recognized with the Hitachi Scholarship Award in 2013 and the DIES ITB Teaching Award in 2025. Friends, let us all welcome Dr. Putri.
Okay, hello everyone. Thank you very much, Dr. Nathan, for the very nice introduction for my CV. Firstly, I would like to give gratitude to the committee to invite me for this nice nice event. And actually, today I will, like Dr. Nathan introduced, I will share actually some information or some topics related with the Hadamard matrices. So actually, this Hadamard matrices is one of my topic of research from master and until now, but there's less people knowing about these Hadamard matrices. So in this opportunity, I would like to share about Hadamard matrices, not in the detail, but actually a brief history. So hopefully this topic can be a nice topic to be interested for the researcher, actually for the elementary level. So I will share my slides. Is it okay? Is it the slides clear? Okay, thank you very much, Dr. Nathan. So I will begin this talk with the title Classical and Modern Methods for Constructing Hadamard Matrices. Classical means it's around the Hadamard matrices constructed in around 18th century, but the modern methods here means recently, so not modern in computation way, with the you using computer or quantum computing, but in theoretical way, but for the recent work. So what is Hadamard matrices? So Hadamard matrices is actually just a plus minus one matrix of order n satisfying this condition. H times H transpose is equal to n times I. So this Hadamard matrix always have the square matrix, and pairwise, it means that always pairwise orthogonal. This is one of the Hadamard matrix of order 4, one of example. So you may see that they are all only plus minus 1, only have the element of plus minus 1. So actually, we have the Hadamard conjecture. This is still an open problem. So the Hadamard matrix of order 4k exists for every positive integer k. So this is actually equivalent to attaining the maximal possible determinant for plus minus matrix, you may see. So this equality holds. Now I will introduce who is the first time at obtaining the first matrix of the construction of Hadamard matrix. So actually, Hadamard not the first one. It was Joseph Sylvester in 1867 who first invented this construction. So to extend the order of the Hadamard matrices, they use the method called Kronecker product. Hopefully, yeah, everyone know about the tensor or Kronecker constructions. So the first you have, for example, only one element, and then for the next order, you may just do Kronecker product. So you may have 2 power to k matrix. So this is called Sylvester Hadamard matrix, and it always the order always the power of 2. So this one is the first one, the Sylvester. But then Hadamard studied the general problem. So he observed how large can the absolute of the determinant M be for a matrix M with the element is in plus minus 1. So actually there is Hadamard inequality, the famous Hadamard inequality. It said that this inequation hold, and with the equality hold if and only if every entry is plus minus 1 and the rows are orthogonal. So he exhibit example of order 12 and 20. So 12 and 20 is actually not the powers of 2. So this showing new order is actually possible. So after Sylvester and also Hadamard, there was Pele who also tried to construct the Hadamard matrices. Well, because the Hadamard is still a conjecture, so some of our researchers trying to approach to obtain this Hadamard, the order of Hadamard matrices by using many methods. So Sylvester using the Kronecker product, and now Pele used the quadratic residue in the infinite fields, GFQ, with the Q is an odd power prime. So this is actually always be an example in the class of number theory. So this using the quadratic character chi and also Jacob-style matrix. So if you're interested in the number theory, actually these Hadamard matrices also can be approached using some of the number theory. There are the first Pele and also the second Pele. So they construct using the quadratic residue, but the second Pele actually using the another class of matrix called conference matrices. I will introduce it later. So smallest order that not reachable by Sylvester, which is the Kronecker one, and the Pele is 92. So you may see that this Pele is 1933, and let's see how long it will be take until we found until they found the 92. So this is the one of example of the Pele type 1. So you may see if Q is each modulo 3, Q is equivalent to 3 modulo 4 is a prime power, then there exists the Hadamard matrix of order Q plus 1. So this is how to construct the matrix. So you may make a Q plus 1 square matrix order of Q plus 1 using quadratic residue modulo Q. For example, like in the slide, you may have Q is equal to 3 because 3 is 3 modulo 4, and then the order will be Q plus 1. So this is one of the example of the Hadamard matrix by using Pele construction. For the second construction, you may use a conference matrix. So let's see the definition first. I mean the theorem. This is not a definition. A theorem mentioned that if Q is equivalent to 1 modulo 4 is a prime power, then there exists a Hadamard matrix of order 2 times Q plus 1. But to do this construction, you need to know the conference matrix. So simply say that conference matrix is actually similar with the Hadamard matrix. The property of the Hadamard matrix, which is pairwise orthogonal. But in this case, we have the diagonal entries are all 0. And then if you multiply that matrix with its transpose, then it will be equal to n minus 1 times identity matrix. In Hadamard case, we have n times I, but in conference matrix, because the diagonal entries are all 0, then we will have n minus 1 times I. So by using conference matrix, we can have the Pele construction of type 2. So this is one of the example of Pele construction. So first we can make the conference matrix of order Q plus 1 using quadratic residue. And then we can extend it to Hadamard matrix of order 2 times Q plus 1. For example, if Q is equal to 5, then because 5 is congruent to 1 modulo 4, and then we can have the order is 2 times Q plus 1. So 2 times 5 plus 1 is equal to 12. So this is so then we can have the construction of the Pele construction of the Hadamard matrix will be like this. So you can just plug the conference matrix and also the identity matrix as follows. Then you may have the Hadamard matrix of order 12. where the C is just a 6 times 6 Paley conference matrix, and I is the identity matrix of order 6. This kind of construction may known as the plug-in method, because we just plug a matrix, another type of matrix, to this much bigger matrix. So we also call this method like the plug-in method. So but like I mentioned before, Sylvester and Paley cannot obtain the smallest order right in that moment, which is n is equal to 92. So some of the researchers begin to searching the way to find this order 92, and then Baumert, Caalim, Hall used a computer search by using Williamson construction. So actually, the help of the computation was the construction of the Williamson, which is John Williamson, in 1944. So let's see first what Williamson made. The first, so he find a way. So we can have four symmetric circulant and plus minus one matrix. So he found that this ABCD matrix of order M satisfying this equation. So there exists this class of matrices, and then combine with the 4 times 4 block array to build this Hadamard matrices of order 4M. So this 4M times I means identity matrix. So then we can have a Hadamard matrix of order 4M. So this construction actually give the contribution to find the Hadamard matrix of order 92. So this is the nice construction of the Williamson matrices. So like I said before, ABCD is just 4 plus minus 1 square matrices. They circulant and also symmetric. The one that is important that this equality should be hold. So by using computation, we can find this kind of matrices, and then just plug this ABCD to this matrix H. Then you may have the Hadamard matrix of order 4M. Once again, this is plug-in method, and by using this Williamson and also hard computation, they found this 4 times M matrices. But this is actually not cover any of order. Why? Because this matrices ABCD is limited. Not all of M exist in this way. So I will give, this is one of the example of Williamson method. For example, we have ABCD as follows. We can see that so the exciting matrices is the order of prime number, right? So we begin with the M is equal to 3, and then we can find Hadamard matrix with Williamson method of order 12. So Williamson mentions, I will be back to the slides, symmetric and circulant was one of the important role in this case. But let's see, Baumert Hall in 1965. So from so to find 92, it's have the gap around 30 years. And now in 1965, Baumert Hall find actually find a generalization of the Williamson method. Sorry. So they mentioned that just use A, B, C, D, satisfying the same orthogonality condition. So only this condition, and also plug these matrices with this kind of Williamson construction. Then we can have Hadamard matrix. So they make a generalization of the Williamson construction. So this is one of the method. They find A, B, C, D in such way, and they produce Hadamard matrix of order 8. So we can see they are not, I'm sorry, they are not circular matrix, but actually they can produce the Hadamard matrix. So what I have introduced is all related with the plug-in method. So plug-in means that you have a possibility to find Hadamard matrices by obtaining some small matrices with such a property, and then you plug into the bigger matrix. But actually, there are another way for those who like algebraic approach. Turing construct the construction from the Baumert-Hall units for symbol sequence and also complex Hadamard matrix. So complex Hadamard matrix is actually have the same property. If you have a complex Hadamard matrix and you multiply it with its transpose, then it will be equal to n times I, but the difference is that the elements of the Hadamard, for this matrix is complex numbers. So with the root of unity, it will be equal to 1. So this will be, there is a way to find Hadamard matrix from this kind of complex matrix, but I will not further discuss in this session. But you may find in some of the research. And also, if you're interested in different sets and cyclotomy, and this will be also one of the approach that you may obtain the Hadamard matrices. So construction from different sets and also Paley type difference family also have the possibility to find the Hadamard matrices. Orthogonal design products, they use the generalized tensor construction, combining the Hadamard matrices of order K and M into one of order like K times M. So the generalized tensor, actually you may begin with the Kronecker product, and then you may do some generalization to find another kind of a Kronecker product to find the other Hadamard matrices. And then Severi and Yamada in 1992, they also they make a survey, actually a comprehensive survey using Williamson-Turin-Goethals-Seidel array construction. So closing the largest historical gap is actually the order is not so big. It is actually 428. So for decades, n is equal to 428 was the smallest multiple of 4 for which no Hadamard matrix known. In 2005, Taifeh Rezi finally construct a Hadamard matrix of order 428 using complementary sequence combined with extensive computer search. I need to mention that in this talk, this method is actually need the help of the computer search. So we can reduce the time of the computation by using some of property in the theoretical way. So one way that obtained by Karagani and Taifeh Rezi was using the complementary sequences. So actually, these complementary sequences is one topic that I really interest. So I will begin to introduce how to construct the Hadamard matrices from these complementary sequences. So complementary sequences actually have a lot of class. You may see like in graph theory, there are many of class of graph. This also the similar one. So the complementary sequences has the class of Golay sequences. It's called Golay sequences, base sequences, and etc. I will introduce only some of them that is related with my research. So first, I will introduce what is actually complementary sequence. Before we go deep into the definition of a complementary sequence, I will introduce you to the Hall polynomial. Let's say f of the factor a. Let R be a commutative ring with identity and involutive automorphism star, and A be a vector with the length L. And we define the Hall polynomial as follows. So we define as the summation of the AI x power to I. So this is just a usual polynomial actually. And let this notation be a ring of Laurent polynomials over R. In this case, we define involutive automorphism as follows. So they just mapping AI to AI star, where the star means the involutive automorphism, and also x to x power 2 minus I. So we will use these Laurent polynomials, and this is the definition of complementary sequences. So we begin with the n sequences, A1 up to AN. Be a sequence with all entries in R. Then we can say that this A1 up to AN, so this is the set of the factors, will be set of the sequence will be is called complementary sequence if this condition hold. So if we do the summation of FAI times FAI star, then we will have they will be just a scalar in R. So there is no other polynomials with x power to something. So they all are in R. If this hold, then we can have complementary sequences. So note that this A1 up to AN do not necessarily have the same length. For example, this we have 4 sequences, and you may see that they are not have the same length. So now how to construct the complementary sequences? How to construct Hadamard matrix from complementary sequence? Let's begin with the smallest, only just 2 sequence. So let's say A and B. And then we say if this A and B are complementary sequences, then we call it Golay sequences. So this AAB will be is called Golay sequences, and the notation of Golay sequences is GSK, which is K means the length of the sequences. So let A and so for example, let A and B be circulant matrices with the first row A and B respectively. So first you construct A and B. So the first row is the Golay is obtained from the Golay sequence. You make a circulant matrix. Then you may have the Hadamard matrix of order 2 power 2 times n. Sorry, 2 times n with this construction. But please note that Golay sequences is limited. So just only the order only have this order. So of course they not cover all of the Hadamard matrix orders. So we will go to the next class. So the next one we have 4 sequences. Now with the element 0 and plus minus 1. Of course you may give a 0 and plus minus 1, not only plus minus 1 sequence. Then we can say that these 4 sequences will be complementary sequences if in this case T sequences of length n, if they are mutually disjoint complementary sequences. So in this case we notate this set of sequences be with Tn. T means the means the T sequences. So for example, you may see these T sequences of order 7. So they have the length 7. 03 means 000. So you may, on 04 means 4 times. So you may have T sequence of order 7. We interest with the prime number. So T7 is a prime number. So this is good. And then from T sequences, we can obtain much bigger matrix with this kind of plug-in, where this R means one in diagonal entries 1. The reverse diagonal is have the entries 1 and the others are 0. And then by using this green matrix, you may have 4 times n. So now n T sequence of order n will be interesting because they can obtain 4 times n matrix of Hadamard matrix directly. So this construction is actually a nice construction. If we begin with the complementary sequences, it's called Gödel-Seidel's arrays. For the I think this one is the last class that I will introduce today. It's called base sequences. So we have Golay sequence, we have T sequence, and also base sequences. Base sequences also 4 sequences, but they have pair different order. So the first order have the length m, and the first pair have the length m, and the second pair have the length n, but they should plus minus 1 sequences, which is different with the T sequence. And then together they have a complementary property. Then it's called a class of base sequences. We can write is as B S M, n. So we have T n and also B S M, n. This is an example of the base sequence of order 3, 4, because they have the length 3 and also length 4. It's usually we write the smallest one and then the larger one. So like I mentioned before, 428 is the important order right now because this one is the last order that they find. The smallest one is 428. It was found by Karagani and also Taife-Rezi in 2005. How they find these sequences actually begin with the Turing type sequences. I need to mention that these Turing type sequences is actually complementary sequences. And then from you may see there are four sequences, and they make base sequences, and then they construct the T sequence from base sequences, and then from T sequences we can obtain a Hadamard matrix. So this method actually found by theoretical way, so not by using a computer. They using in the theoretical way, and then they prove that there exists such construction. So recently this method to find the Hadamard matrix from complementary sequence actually still on research until now. So this is actually one of the, I may say, modern method because it's just recently until now still on research. So first I will introduce the method. It's called Young multiplication for complementary sequence. Basically, the idea is to combine 2 classes of complementary sequences, and then you may have the target is you find the T sequence, because if you have T of order n, then you may have the Hadamard matrix of 4 times n, right? So now the target is to find the T sequence, not the Hadamard matrix. So to find this T sequence, there are many methods. Young in 1983, it's also, actually this one is, much older, but Young found it by using direct construction. So by using direct construction, so he find the exact sequence of order 2s plus 1 times m plus n. And then the next one, he find direct construction of 13 times m plus n, where this mn is an order of base sequences. So then we try to generalize the construction of Yang by using so we try to find so how it works. Then we begin with this definition. So not using f, but not using Laurent polynomial, but we define this psi of A like as follows. So what is the difference with the f? Well, the difference is now we have x power to minus something. If we can easily see that there are x power to minus something, while the usual f Laurent polynomial, there is no x power to minus thing. Well, actually, this seems obvious, but actually for the computation, it is much reduce the computation way. So we define this psi A as follows. And so we compute the complementariness using psi rather than using f. So actually, why this psi is important? Because we want to use rather than sequence, we want to extend it to a matrix. So for in the matrix, actually the computation is much more easier. So now let's A be R times or R power to m times n matrix. So it's matrix of order m times n. And then we define psi of A x comma y as follows, where this psi of AI means from the last definition. So there is a psi for sequence and psi for the matrix. So we define in this way. And then we recall the famous identities called Lagrange identity. Lagrange identity mentioned that if we have A, B, C, D, like in a slide, is in R, and then we construct Q, R, S, T as follows, then we can have this identity. Why this identity is important? Because it is very nice if we have complementary sequences, and then A, B, C, D also complementary sequences, E, F, G, H also complementary sequences. Then we can have, for example, if we have this one is base sequences, then we can find another sequences. So we can have like 4 times something or m times something. So this is nice if we have primes times primes. Then we can have primes times primes, prime time 4, which is the existence of the Hadamard matrix. So our strategy goes this way. So first, we try to so this is a joint work with Professor Munemasa from Tohoku University in that moment. So we try to construct the QRST. They are a matrix, and then we construct in this way. And finally, we can extend this Lagrange identity. Use Lagrange identity to find this thing. So this equality holds means that this matrix QRST can be equal to this two term of this multiplication things. So we may focus on 4 or maybe prime complementary sequence, but prime numbers, and also complementary sequence with the prime numbers. But recently, actually, around 2010, Djokovic find define this kind of thing. So first, he mentioned normal sequence. Normal sequences is actually three sequences of order, three sequences with the element 0 and plus minus 1. And they have such property. So B, C are disjoint, and A is plus minus 1. So it means A is plus minus 1 and BC is 0 and plus minus 1 sequence. And they have together a complementariness. Then it's called normal sequence. And also a near normal sequence is actually a base sequences, but with some kind of property that mentioned in here. So, well, basically near normal is base sequences. And then Djokovic mentioned that defined a Young number because it's actually developed from the Young result. Young number is an odd integer 2s plus 1 such that the near sequence or near normal sequence is not empty. So they find, so in 2010, if y be an odd, if y is an odd positive integer and y is smaller than 73, then y is a Young number if y is not equal to this number. So 35 is actually the smallest in that moment. I think until now, the smallest number, which is a near sequence and near normal sequence, does not exist, is empty. Why this number is important? Because we have this one is 2s plus 1. So this 2s plus 1 can be attached in here. So if you have 2s plus 1, so 2s plus 1 is odd numbers, and then you may apply base sequence in here. So you apply base sequence in here, then you may have 2s plus 1 times m plus n, which is the order is quite interesting from to obtain 2s plus 1 times m plus n times 4, which is the order of Hadamard matrices. So until now, actually, this is the summary of the timeline. I have just introduced Sylvester. Hadamard introduced the determinant of the bound. Pele, Williamson, Baumert, Golomhal, Baumert-Hall, which is using Williamson type matrices, and also so in 1970 they find the way to obtain Hadamard matrix from the complex complex Hadamards, like I said before, means the matrix have the element in complex number. In 2005, they find 4028. The order of Hadamard matrix is 428. So what the next order, the smallest order, is 668. 668 remains open, so we still don't know how to use it and how to find it, and hopefully from the complementary sequence there is a way to find. And actually not focus on the construction. We can also do the research to find the asymptotic result. So in 2012, Ivan Levinsky proved an asymptotic existence theorem for Hadamard matrix. So he find that for any order, any odd integer p, there exists Hadamard matrix of order 2 times t times p, where p is odd, and this is quite interesting for all t with which is bounded by this number. So the interesting things is that his construction actually using a lot of algebraic number theory. He used sign groups. So the sign groups is one of the class of the group and have the have the some properties, and it combined with a zero autocorrelation sequence. We call it this is complementary sequences. So he combined the sign groups and also complementary sequences. Then he find this bounded this. So yeah, this method is actually quite nice, and this extend the classical research by Paley and also Sylvester, providing new infinite families of Hadamard matrices. I see in his thesis the open problems of to extend this result actually using pure number theory. So I think if you're interested in number theory, it will be nice to see deeper in this research. So this is Hadamard's inequality that I mentioned in the first slide. So this what the contribution of this Levinsky result. So Levinsky actually confirms that Hadamard matrix exists for infinitely many orders of n. Therefore, the bound of n power to n over 2 is achievable infinitely often. So this is actually strength the asymptotic evidence for the Hadamard conjecture. So rather than find the construction, if you interest in the asymptotic result, then it also can be possible, because until now this Levinsky result is the newest one until now. And because this is using the sign group, which is also introduced by Kragen, I think if you also interest in the algebraic number theory, this one is also one topic that you may see. So last, what is the application for Hadamard matrix? So if you're interested to use the Hadamard matrix, actually coding theory use a lot of Hadamard matrix. So for example, Hadamard codes, error correcting codes, if you know Reed-Muller, inside of the Reed-Muller, you may have Hadamard matrix. Recently, my students have a research on compression also using Hadamard matrices. So there are a lot of application in coding theory. In statistics, we use optimal design for experiments. For example, Yates weighing design. In signal processing, we have Walsh-Hadamard transform and also CDMA sequences. In quantum information, we use a mutually unbiased basis. Mutually unbiased basis can be approached in theoretical way, also for complex Hadamard matrix and many more in Hadamard gate. So for yes, I think this is my last slide. I will update that yesterday, actually, there is a talk from the quantum computing professor, which mentioned that the order of Hadamard matrix of 668 actually is now on the way to search by using quantum computing, and it might be a pair in 2029. So let's see if it exists or not. Okay, this will end my talk. This is my reference. Thank you very much for the time.
Thank you very much, Professor Pritta, for your wonderful presentation. So we need to wait until 2029 to know the answer to
Yeah.
668.
Let's see.
Okay.
Let's see if the computer can search, or it is possibly say yes, no, or they don't know, right?
Okay.
So let's see.
So there's a question in the chat about
Okay.
application, but you already mentioned some applications.
Yeah.
So the participants are invited to ask questions about the talk. And maybe you can also ask, because there are many students, you can ask Professor Pritta, like things about studying abroad or
Okay.
doing research in Bandung, etc. So let me ask the first question. So you explained this process of starting with a Turing type sequence, and then it became a base sequence, and then finally a T sequence. Will
Yeah.
this all the way to obtain a Hadamard matrix? Will this always work if you start with a Turing type sequence?
Okay, thank you very much for the questions. Uh, Let me share the slides that related with Professor Nathan's questions. So from here,
Yes.
yes. So if there exists this the first Turing type sequence, the only way is you need just to find the existence of the order of these Turing type sequences. If there exists, then this always work this will lead always to Hadamard matrices. But the problem is that is there exists for any order of this Turing type sequence, then it's also a conjecture. So Turing type sequence means you have 4 sequences of order 36, 3 sequences of order 36, and also the other is 35. And then with this way, we can have Hadamard matrix. Why they using Turing type? Well, actually, in that moment, 428 was the open problem. So many people try to find a way, well, actually, some using another method, but this sequence, Turing type sequence, finally works to obtain the Hadamard matrix. Yes. And actually still a conjecture for all. If you find all order of Turing type sequence, then you finally answer the conjecture.
And of course, for people doing combinatorics, probably the most combinatorial approach will be to study complementary sequences.
There are many ways.
Other
So
methods.
yes. So for example, this one is the these are methods to obtain Hadamard matrix. So for example, if yes, for example, Professor Nathan like to do number theory, then number theory can be a contribute in the different sets and cyclotomy. So they also trying to find not by using the make a direct construction, but using different sets. And also the Paley was the one using quadratic residue. So this one also can be one that you may approach using number theory.
Okay, thank you. Are there questions from the audience? Maybe from students or researchers?
Okay.
Well, if I may ask another question. So it's actually not only quantum computers that are helping mathematical research now. There's also
Yes.
AI. So
I think yes. I don't know. But maybe. Let's see. Let's see 2029 if they publish a paper. Well, actually, for the order of 92 is approached by using similar way. Yes, we know that in that moment there is no AI, but using the hard computer uh, search, and they obtain 92. So if you want to try to find the 668 or another next smallest order, maybe we need to do a collaboration, so we can approach by using in mathematical theory approach and simplify the properties, and then using the quantum computing. But maybe because there is an AI, well, I have no comment on that one.
okay.
Thank you very
Do
much.
we have other questions? Yes, Professor Melchor, please go ahead.
Yeah, I think what the participants are interested, maybe partly or a little, is that Dr. Prita, are you available for research collaboration? Like, could we request you to become a thesis co-advisor of research of our undergraduate students or master's students, something like that? Is
Yes,
that
of
okay?
course.
Are you open? Okay,
Oh,
so
yes, yes.
see,
Yes,
yeah,
very okay, very welcome. Actually, I'm very happy to to be collaborated if there are any, because like I mentioned before, this yeah, this topics is actually not much known, so just only few people that really want to do the research in this Hadamard metric. So very welcome to be one of the collaborator of this research. And
yeah. So
actually, I
there.
have this background is ITB. So ITB is in Bandung, Indonesia, in West Java. Uh, this is the one of the, maybe it's nearly like in the Philippines. We have buildings with the green, lot of green area. So please don't worry if you want to visit for maybe exchange to Indonesia or to ITB. The environment is similar, so but maybe new friends can be find in this way. So this is the campus, my campus in IPB. Maybe this that I want to promote that one.
Okay, maybe
Okay,
one
so
more question before we go.
okay.
Thank you very much for the question. Yes.
Okay, well, it seems there are no questions. So maybe they can message or email you later.
Yeah.
So we will now be moving to the next part of the program. But again, we would like to thank Professor Pritta for a very wonderful presentation.
Thank you very much for the invitation. Thank you very much, everyone.
Okay, thank you very much, uh, Dr. Prita, Putri, for your hello. So, sorry. Let me get my hello. Okay, so my AirPods is better in picking up my voice. Okay, so thank you very much, Dr. Prita Putri, for sharing your expertise on Hadamard matrices, and for Dr. Jonathan Caalim for introducing Dr. Prita and moderating the question and answer. So we're now down to the last part of our program, which is closing ceremonies. So let's award the certificates to our guests. So I was told that someone will show the certificates, share the certificates on the screen. So there. So let me read the citation. So Mathematical Society of the Philippines, Region 3, Certificate of Appreciation. This certificate is proudly presented to Jos P. Sebastian, Central Luzon State University, Philippines, in grateful recognition and sincere appreciation for serving as a resource person in the Southeast Asian series on mathematical research with the theme Current Trends in Discrete Mathematics, organized by the Mathematical Society of the Philippines, MSP Region 3 chapter, held on July 18, 2020, 2026 via Zoom. So signed Nancy Mati and Secretary MSP Region 3 and Dr. John Rafael Antalan, President MSP Region 3 signed. So we're going to send the certificate with actual signature. So we haven't included it there for data privacy purposes. So next certificate. So with the same citation, this certificate of appreciation is presented to Pritta Putri. So Institut Teknologi Bandung, Indonesia. So in grateful recognition and sincere appreciation for serving as a resource person in the Southeast Asian series on mathematical research with the theme Current Trends in Discrete Mathematics, organized by the Mathematical Society of the Philippines, MSP Region 3 chapter, held on July 18, 2026 via Zoom. Signed Nancy Ilmati, Secretary, MSP Region 3 chapter, and signed John Rafael M. Antalan, so President MSP Region 3 Chapter. So thank you very much for our speakers for your effort and preparing your slides for the today's event. So Josh, P. Sebastian, and Dr. Pritta Putri. Okay, thank you very much for your time and effort in sharing your expertise. Okay, yeah, photo op. So if it's possible on your end, so let's have a photo op, of photo opportunity. Yeah, by the way, I wasn't able to mention earlier, so my my polo, I bought this from Indonesia. Okay, so let's do it. So how many slides do we have? So by the way, update on the number of participants. At the start, so we had 50. So we now have 114. Yeah, thank you very much for coming and joining the event for today.
Sir,
So who will be
for the
taking?
evaluation as well, sir, kindly remind everyone, sir. Thank you, sir.
Yeah, for the evaluation, yeah. So Ma'am Yolanda Roberto posted the evaluation form link in the group chat. So kindly fill out the evaluation form link. So once you fill it out, I think you will get your certificate. If not automatically, I think it's automatic. So if not, just wait for a few days. But I think it's automatic. So there, you have also the QR code of the evaluation form and the MSP membership on your screen. So you could take a photo of it or snapshot, something like that. Okay. To fill out the evaluation form and possibly join MSP. For those who are in the Philippines, I think abroad also, yeah, it's possible. Okay. So can we now have the photo opportunity?
Yes, sir. Thank you, sir.
Oh yeah. So I'll be the one taking the screenshot. So how many pages is this one? Okay. So first slide or window. Yeah, again, if it's possible, you can open your camera on your end and smile. Okay, that's first window, second window. Okay, next window. Okay, the next one, there are so many. Okay, next one. Okay, next one. Okay. One more. Okay. So there, thank you very much for attending this day's event. So for the closing remarks and reminder, so may I give the floor to Dr. John Rafael M. Antalan, the President of MSP Region 3. Sir JR, for the closing remarks.
Thank you very much, Sir Melchor. So again, to our invited speakers, Dr. Putri and Sir Josh, thank you very much. And to everyone present here today, maraming salamat po. And with that po, stay tuned po for the upcoming events of the MSP Region 3. We will be posting our future events in our Facebook page. With that, maraming salamat at take care always. Ingat po tayong lahat. Thank you po.